Hello everyone, welcome to NPTEL online certification course on fundamentals of food process engineering. We are discussing about mechanical separation technique since the last two classes, and today also we will continue with the same topic. So, in the last class we have seen the filtration mechanism, the principle behind calculation of the pressure drop through the filter cake and the filter medium, okay, and what are the important factors that going to affect the rate of filtration in a process, okay. And today we will see few more cases of filtration and also we will solve a few problems on that. So, let us start. First we will discuss now that constant pressure filtration. So, we have seen normally that the pressure may change because of the deposition of the cake on the filter medium, okay. So, if the deposition increases, so obviously the pressure drop will increase, okay. Now, if the pressure drop increase, that will going to affect the rate of flow. So, two cases may occur, either the rate we want to make constant, okay, or we want to make the pressure drop constant, okay. So, both the cases, what will be the method of analyzing the parameters of the cake and also the filter media, that we will see. So, first we will see the constant pressure filtration. In that we will start from the basic equation of basic equation for rate of filtration that we have calculated, that was our linear velocity. So, that equation, if you remember, that was V, that is equal to dV by dt divided by A, that is equal to minus delta P. Delta P includes both Pc, that is pressure drop through the cake, plus delta Pf, that is pressure drop through the medium, divided by, there was okay. So, there was mu into alpha Cs into mu into alpha Cs into V by A, plus there was mu into Rm, okay. This was the equation. Now, what we did here is that we have reversed this equation, we have taken A this side, okay. So, it has become A square here, A square into delta P. So, this A and this A is coming with this delta P. So, we are getting A square into minus delta P into V plus mu into Rm divided by A into delta P. So, we have reversed this equation in terms of dt by dV now and have taken this A to the other side, and finally, we got this equation, that is dt by dV, that is equal to mu alpha Cs by A square minus delta P into V plus mu into A, mu divided by A into minus delta P Rm, okay. And this we have further simplified in the form of a Kp into V plus B. Now, it has been interpreted as dV amount of filtrate has been passed through the filtration system in a dt time through the cake as well as through the filter medium. A is the cross sectional area of the filter media, mu is the viscosity of the filtrate, alpha is specific cake resistance of the cake that has been deposited, Cs is the Cs is kg of the solid present per meter cube of the filtrate, capital V is the volume of filtrate that has been passed through in time t, minus delta P is the total pressure drop across the flow line, that is through the cake plus the filter media, and Rm is the resistance of the filter media. Now, we can express this as Kp into V plus B. So, Kp will be mu into alpha Cs by A square minus delta P. Similarly, B will be mu divided by A minus delta P. So, Kp, the unit of Kp will be second per meter to the power 6 and the unit of B is second per meter cube. Now, for constant pressure, constant alpha, that is specific cake resistance, we need to have constant, and incompressible cake, because if it is compressible then obviously the pressure will not be constant. So, that is why we consider that incompressible cake. Capital V, that is the volumetric flow, volume of the flow that has been taken place in time t. These are the only variable in this equation. Okay. So, if we want to maintain the constant pressure, so alpha we need to fix, okay, and incompressible cake we have to assume. Only thing V and T, these are variable. So, to integrate this equation to obtain the time of filtration in t seconds. So, if we take dt and the other side we take dV and we integrate, so then we need to find that the time of filtration in t second. So, for that from initial time t equal to 0 to t equal to t dt, that is equal to integration initially at the start when no volume has been passed through to the final volume V, Kp into V plus B into dV. So, we are getting the expression as T equal to Kp by 2 into V square plus Bv. So, this is the time required for constant pressure filtration. Okay. Now, we can also represent this in the form of T by V, that is equal to Kp by 2 V plus B. So, why we want to express in terms of that, because in any experiment when we want to find out that what will be the parameters of Kp and B, and we have the data only the different T and V, okay, or different volume of the flow that has occurred at different time. So, getting this kind of expression we can very well get a linear pattern. Okay. So, if I plot T by V with respect to V, so we can very well get a linear equation in the form of mx plus c. So, from the slope and the intercept we can have the values of other parameter that is required here. Okay. So, this I have already mentioned that the V is the total volume of filtrate that is collected in t second. So, V is in meter cube volume of the filtrate. So, then to calculate the time for constant pressure process where alpha and Rm is necessary, data of the V collected at different time t, these are obtained. So, with that I can plot T by V, that is S per meter cube divided by V, that is filtrate volume in meter cube. So, then we can get one straight line. The slope will give us the value of Kp by 2 and intercept will give the value of B. And since the Kp by 2 and B, these are related with alpha and Rm as we have seen in the previous equation. So, Kp is equal to mu into alpha Cs by A square minus delta P and B equal to mu divided by A into minus delta P. So, delta P are constant, we can get that. So, area is known to us. So, then alpha value and here the Rm value mu into Rm divided by A into minus delta P. So, this way we can calculate. Now, okay. So, this is how for the case of a constant pressure filtration we can calculate the time and all other parameters like specific cake resistant and the resistance due to filter media. Now, coming to the next case, that is constant rate filtration. So, when the filtration starts, actually that is the initial stage of filtration, what will happen that it frequently happen that filter resistance is large relative to the resistance of the filter cake. Okay. Filter medium resistance is large compared to the resistance of the filter cake, because the cake is thin in the initial stage, right. So, this condition, the resistance offered to the flow is virtually constant and filtration proceeds at a more or less constant rate. So, initially when the deposition of the cake is not there, at the onset of this deposition, that time the resistance offered by the filter media is high compared to the resistance of the cake, and constant rate of filtration prevails. So, this can be seen as we have taken the same equation, that is the related to that velocity in terms of dV by dt divided by A, that is related with delta P and mu alpha Cs, mu into alpha Cs into dV by A plus mu into Rm. So, that equation we have taken, and in terms of pressure drop and V, now we have plotted this. So, what we are getting? We are getting that minus delta P equal to mu alpha Cs by A square into dV by dt into V plus mu Rm by A into dV by dt. This is equal to we can write it in terms of kV into V plus C, where kV is mu into alpha Cs by A square into dV by dt, and C is equal to mu into Rm by A into dV by dt. So, kV the unit is in Newton per meter to the power 5, and C, unit of C is Newton per meter square. So, for incompressible cake, kV and C are constant characteristics of the slurry. For incompressible cake, incompressible cake, kV and C are constant characteristics of the slurry and cake, rate of filtrate flow and so on. So, kV and C will be constant for the slurry, for the cake and for the rate of filtrate. Now, a plot of pressure, that is delta P, versus the total volume of filtrate collected, that is V, gives a straight line. So, in the previous case, when we have plotted the constant pressure filtration, that time T by V was only the variable. So, T by V was plotted with V. Now, since we are dealing with the constant rate filtration, so pressure drop varies here with the volume V. So, that we are plotting now to get a straight line. Okay. So, for a constant rate, since dV by dt will be fixed. So, the slope of the line is kV and the intercept is C. Okay. The pressure increases as the cake thickness increases, and the volume of the filtrate collected increases. So, with that the pressure will increase, and the equation can also be rearranged in terms of delta P and time t. As we have done for the delta P versus V, we can calculate delta P and t as variable, and any moment during the filtration, the total volume V is related to the rate and the total time t by the following equation. So, V equal to t into dV by dt. So, rate of filtration into time, that will give us the total volume of the filtrate that has been passed through, and minus delta P into mu into alpha Cs by A square into dV by dt whole square into t. Just we have replaced that V with this expression, and mu into Rm by A into dV by dt. So, now delta P with respect to t we can plot. Okay. and here the specific cake resistance is not a constant. So, here we will solve one problem which is based on the constant pressure process. So, the data for a slurry in water. So, it is a slurry in water at 298.2 Kelvin, that is 25 degrees Celsius. These are reported as follows at a constant pressure process where the pressure was 338 kilonewton per meter square. So, 338 kilopascal, this was constant. The filter area of the plate and frame press was 0.0439 meter square, and the slurry concentration was Cs, that is kg per meter cube, that was 23.47 kg per meter cube. Calculate the constant alpha and Rm. So, specific cake resistance and filter media resistance from the experimental data given, where T is in time in second, okay, in second, and V, which is the filtered volume collected in meter cube. So, let us see first what is the data given. So, here is the data. So, we are getting, as we have already know that for the constant pressure process, pressure is constant, only the variable is time t and volume V collected at that time. So, these data we are having starting from 4.4 second to 107.3 second, and V varies from 0.498 into 10 to the power minus 3 meter cube to up to 5.009 into 10 to the power minus 3. Okay. So, this is the data. Then what we need to do is, for the solution, first this is T, this is V, we need to have the data of T by V, okay, because the equation for a straight line if you want to make, we need to plot T by V with respect to V. So, T by V we have calculated, this is T by V into 10 to the power minus 3, this is the data. Next is, we need to plot this T by V versus V. So, here in our x axis volume of the filtered V into 10 cube, that we have plotted, and in the y axis we have plotted T by V into 10 to the power minus 3. So, this is that. Now, we are getting a straight line. So, from that the intercept is calculated B, that is equal to 6400 second per meter cube, and the slope, that is Kp by 2. So, Kp by 2 is 3.00 into 10 to the power 6 second per meter to the power 6, hence Kp we are getting 6.00 into 10 to the power 6. Now, we have calculated that Kp and B, then what is the condition given, that at 298.2 Kelvin the viscosity of the water we need to use. So, this we can get from chart if not given in equation. So, this is 8.937 into 10 to the power minus 4 Pascal second. So, we need to substitute this data, this is the value of mu, we need to substitute into this two equation. We know the expression of Kp and B, Kp is mu into alpha Cs by A square into delta P, mu is this one, that is the viscosity at a particular temperature, at what temperature the flow is occurring. So, that we can take from the chart. Alpha we need to find out, specific cake resistance, Cs is given, area given, delta P given, which is constant. Here also this will be mu into Rm by A minus delta P. So, mu is given, A is given, delta P given, Rm we need to find. So, we will put this data. So, Kp is equal to 6 into 10 to the power 6, that is equal to mu alpha Cs by A square minus delta P. So, mu is 8.937 into 10 to the power minus 4 Pascal second, alpha into CS is 23.47 kg per meter cube, by area is 0.0439 meter square. So, this square, and delta P is 338 into 10 to the power 3. This is given in kilopascal, in the equation we are putting in Pascal. So, this is, then next is alpha, which is 1.863 into 10 to the power 11 meter per kg, that we are getting from this expression. After that we will put the value in the form of B, that is 6400 into mu into Rm by A minus delta P. So, mu is given, Rm we need to calculate, this is given. So, what is the value of Rm now? Rm is 10.63 into 10 to the power 10 per meter. So, from a constant pressure process, now we are able to calculate the specific cake resistance and also the filter media resistance from the time and volumetric flow data. Okay. Now, next is types of filter and filtration mechanism. Now, the basic requirement for filtration equipment are, what are the things needed? First is the mechanical support for the filter medium, flow access to and from the filter medium, and provision for removing the excess filter cake. And filter selection, what will be the basis of selecting the different kind of filter? The most important factor, as we know, is specific cake resistance. Okay. So, if the cake has to be washed, the rotary drum is to be preferred to the rotary leaf. So, rotary drum is better, and if a high degree of washing is required, it is usually desirable to repump the filter cake and to filter a second time. For free filtering materials, a rotary vacuum filter is generally most satisfactory. And filter media, the function of the filter medium is generally to act as a support for the filter cake, and the initial layer of the cake provide the true filter. So, filter must meet the following requirements, that is, it must retain the solid to be filtered, giving a reasonably clear filtrate. It must not plug or blind, that is, the particle of the slurry should not clog the pores of the filter medium. It must be resistant chemically, that means it should not react with the slurry which is coming onto it, and strong enough physically to withstand the process condition. It must permit the cake formed to discharge cleanly and completely, and sterile filtration imposes a special requirement, since the pore size must not exceed the dimensions of bacteria or spore. So, these are the requirement. And what is filter aids? The object of the filter aid is to prevent the medium from becoming blocked and to form an open porous cake. So, reducing the resistance to flow of the filtrate, okay? Because if the resistance is increasing, flow rate will decrease. That is why the particle must be inert, insoluble, incompressible, and of regular shape. Filter aids, for example, the diatomaceous silica, perlite, wood cellulose, or other inert porous solid are used as filter aids, and filter aid may subsequently be separated from the filter cake by dissolving away the solid or by burning out the filter aid. If solids have no value, they and the filter aid are discharged together. So, because filter aids are getting mixed up with the solids or the deposition, so both are discarded if they are not required, if the solid cake is not required. So, filters are divided into three main groups: cake filters, clarifying filters, and cross flow filters. The features, if we look into, the surface filters are used for cake filtration, in which the solids are deposited in the form of a cake on the upstream side of relatively thin filter medium, and cake filters separate relatively large amount of the solid as a cake of crystal or sludge as illustrated. Now, the filter medium has a relatively low initial pressure drop in this particular cake filter case. So, here we can see that the cake medium, that is the pores are very small, all the particle will form a cake initially on the filter media. And the second case, which is clarifying filter, here the pores are generally big and small particles will come down through the floor easily, come down through the perforations of the filter medium very easily. And third is the case of the cross flow filter. So, in a depth filter, the particles are smaller than the medium opening, and hence they proceed through the relatively long and tortuous pore. So, that we have seen in the clarifying filter case, and they differ from the screen in that the pores of the filter medium are much larger in diameter than the particle to be removed. In case of screen, we have seen that the particle which has passed through, we assume that the diameter, equivalent diameter of the particle is just like the just equivalent with the screen opening size, okay, that is that equivalent diameter of the screen opening. But here the particle are very much smaller than the size of the openings or the perforations. And clarifying filters remove small amount of the solid to produce clean gas or clear liquid. The solid particle are trapped inside the filter medium or on its external surfaces. In cross flow filter, the feed suspension flows under pressure at a fairly high velocity across the filter medium. So, we will stop here and we will continue in the next class. Thank you.